Hello everyone, welcome to mini courses. I'm Yan from the G11 SIG of the openEuler community. In this episode, I'm going to talk about a tracing framework called Ftrace. Ftrace is the official tracer of the Linux kernel that helps system personnel see what is going on inside the kernel. Although its name function trace refers to the ability to record function calls during kernel running, it is now actually a tracing framework of several assorted tracing utilities that help with kernel debugging and performance analysis. For example, if you want to view the system scheduling status over a certain period, or the execution flow of a task's functions in the memory, Ftrace is a great option. Let's take a look at the Ftrace framework. The Ftrace framework consists of the Ftrace core, RAM buffer, debug.fs, trace points, and various tracers. The Ftrace core manages all Ftrace functions, including tracer registration and RAM buffer control. The RAM buffer is a carrier of static and dynamic trace data. Debug.fs provides an interface for the user space to use Ftrace. Trace points are probe points inserted into specific functions in the kernel code to trace certain kernel operations. And tracers are plugins that implement different tracing functions. For example, the function tracer traces all kernel functions. The wake-up tracer traces and records the maximum latency required for the highest priority task to be scheduled, and the nope tracer traces nothing. Using the function tracer as an example, let's see the overall Ftrace process, which is divided into 4 steps. The first step is to insert trace points into target functions. Then, dynamically collect and manage the trace points. Trace calls to the target functions. And the last step, register Ftrace callback functions. Let's go to the first step, insert trace points into target functions. To insert a trace point, use the GCC PG option to add a mcon call after the prolog at the entry of each function. The PG option inserts call mcount for x86 platforms and BLMcount for ARM64 platforms. I'll use BLMcount and the kernel schedule function as an example to describe the trace point insertion process. The left figure shows part of the compiled schedule function, and the right figure shows the function after the PG option is inserted. You can see that 2 instructions are added. The first instruction copies x30, an instruction register that records the current call address, to x0. The second instruction is the BLMcount call of the corresponding trace point. There are 2 trace point insertion modes. The first mode is static Ftrace, which inserts trace points by redefining the mcount function. Once enabled, trace points will be inserted into all functions in the kernel, except no trace, online, and other special functions. In doing so, there are huge performance overheads and a large number of logs, making it a poor choice for tracing only some of the functions. The other mode is dynamic Ftrace, which can trace only specified functions. Dynamic Ftrace replaces BLMcount with nope for functions you don't want to trace. This requires that the trace points be collected and managed in a unified manner. Now let's move on to the second step, dynamically collect and manage the trace points. Ftrace uses these 2 scripts to collect trace points in the kernel. During kernel compilation, each time a .c function file is compiled, a relocatable .o file is generated, and the record mcount script is then called to read the relocation section of the .o file, find every mcount call address, and put the address to the temporary buffer. After all mcount call addresses are found, a mcount location section is added to the .o file to write the addresses. To collect mcount call addresses, or trace point locations across all .o files. We define the start mcon location and stop mcon location, two variables in the vmlinux.lds.h script to enclose all of the addresses. For example, place the mcon core addresses in the three .o files on the right of the left figure between start mcon location and stop mcon location to the vmlinux file on the left. Then perform relocation to obtain the virtual addresses of these mcon cores. Now let's move on to the next step, trace calls to the target functions. During kernel boot, all BLMcon calls are replaced with nope. In this stage, ftrace is disabled. To enable ftrace and trace specific functions, it is necessary to find the trace point locations of the target functions. This can be easily achieved with traversal. Ftrace also builds a dynamic ftrace struct to save the enable or disable status of each trace point, and uses ftrace pages to save the data from all dynamic ftrace structs. After this step, all data in the mcon location sections of the vmlinux file is migrated to the ftrace pages, after which the mcon location sections are released. Data in ftrace pages is better organized and easier to locate. In dynamic ftrace on the ftrace pages, IP indicates the trace point location and flag indicates the trace point status, which can be enabled. The function is being traced. Register, the function needs to save registers. Register enable, the function is being traced and needs to save registers. IP modify, the IP address is allowed to be changed. Disabled, the function is not traced. Direct, there is a direct function to call. To enable ftrace of a specific function, you only need to modify the flag field in a dynamic ftrace struct of the function's trace point. For example, in these two figures, the trace point flag of the schedule function is set to register enable to enable the function trace and make the function save registers. In this case, the ftrace register corner entry is added. The trace point flag of the yield function is set to enable only the function trace. In this case, the ftrace caller entry is added. Take the ftrace caller as an example. This code is generated after ftrace is enabled, in which mcon enter obtains the target function's program counters and link registers, and puts them into the x0 and x1 registers, and ftrace call uses nope as a placeholder. After ftrace call is registered, nope will be replaced by a bl command that jumps to the handler function of the corresponding tracer. It returns the trace information to the tracer, and then the tracer writes the information to the rim buffer. Ftrace call is actually the callback function we need to register. In the last step, we register ftrace callback functions. Ftrace uses the register ftrace function to register callback functions. During registration of a specific callback function, the register ftrace function is called to add an ftrace OPS struct that contains the callback function information to the global list, the ftrace OPS list. This process registers the callback function in a struct and replaces nope under ftrace call with the corresponding bl command of the corresponding tracer. Tracers, function graph, blk, and kprop use static ftrace OPS, while perf uses dynamic ftrace OPS. Static ftrace OPS structs are allocated during kernel boot and can be directly used, whereas dynamic ftrace OPS structs are dynamically applied before callback function registration. This figure shows the content of an ftrace OPS struct, in which the func field holds the callback function to be registered, which corresponds to the ftrace call in the ftrace corner entry. The flags field corresponds to the flag field in ftrace pages. The function to be traced is placed in the hash table. Let's see an example. In the figure on the left, we have jumped to the Ftrace caller entry of the schedule function, but the Ftrace callback function has not been registered. In many cases, a function is not only traced by only one user or OPS. If two or more users want to trace the function, Ftrace provides a public handler function, BL Ftrace OPS list func, to iterate or register OPS on the Ftrace framework and determine which OPS need to trace the target function. If some of the OPS do, the BL Ftrace OPS list func can call their callback functions to return the trace information. This closes the entire trace loop. That's all about the Ftrace framework and the overall Ftrace process. If you want to learn more about Ftrace, visit our official website or the open source community. I hope you enjoyed today's course. See you next time!